So, still on the applications of complex numbers, we'll be talking about fractals and complex dynamics. Yeah, this is where complex numbers really get very artistic and very beautiful. So tighten your seatbelt and get ready for the beautiful visuals you are going to see along the line. So fractals and complex dynamics. We've talked about complex numbers, we've talked about complex functions. So a complex number z is x plus iy, or if you like, a plus ib, if you like. But I think x plus iy, right? And then you have a complex function, which is which is f of z, and it can take different shapes. It could be 1 over z, it could be, modulus of z, it could be anything at all. Do you understand? So like that. So you have complex number z equals x plus iy, then f of z, that's complex function. Now we're going to talk about complex dynamics in addition to fractals. So first of all, what are fractals, right? A fractal is a geometric object that exhibits self-similarity. So it's more like you have a tiny thing and then you duplicate it over and over and over and over again. So it exhibits self-similarity. It has fine structure at arbitrarily small scales, and it is generated by iterative processes. It's more like you have a tiny snowflake and you have tons of snowflakes like that. That's a very close idea to the idea of fractals. So the key idea is that fractals arise from repeatedly applying a function. So if you apply a function repeatedly, then you have fractals. So then we talk about iteration and dynamical systems in this regard. A dynamical system studies how a point evolves under repeated application of a function. Well, I have a playlist on dynamical systems. You want to check that out. So in case you need to learn about dynamical systems, where you talk about things like orbits and planes and all of the planar dynamics and all of those things. So a dynamical system studies how a point evolves under repeated application of a function. So a general form of dynamical system will be something like x sub n plus 1 equals f of x n. So here now when n is 0, you have x1 equals f of x naught. When it's then n is 1, you have f of x2 equals f of x1, and it keeps going like that. So a typical example will be xn plus 1 equals xn squared minus 1. So if you start with x naught equals 0, right? So it means you have x1 equals x naught squared minus 1. So, in that case, um, so if x naught is 0, so x1 in that case will be x1 equals 0 x naught squared minus 1. That's 0 squared minus 1. So that will be minus 1. So now x2 will now be x1 squared minus 1. So x1 is already minus 1. So minus 1 squared minus 1, that will be 0. And then x3 will be x2 squared minus 1. x2 is 0. So 0 squared minus 1, you go to minus 1. So it's like you have minus 1, 0, minus 1. It keeps going like that. So this now produces a periodic orbit. As you keep applying that, then you keep having that up and down motion like that. So you have a periodic orbit in that regard. So when we come to complex numbers, right? Like I said, a complex number is z equals a complex number is z equals a plus bi, or if you like, a plus where x plus yi or whatever. So a complex number is z equals a plus bi. So the magnitude of that complex number, modulo z, is actually square root of a squared plus b squared. And then we study dynamics in the complex plane, and this leads to fractals. Okay, so we've talked about that. Those are complex numbers. Now, what about complex dynamics? Now, we study iteration of complex functions like z sub n plus 1 equals f of zn. And the most important example will be zn plus 1 equals zn squared plus c. So this c has a lot to determine. So this generates two kinds of sets. It can generate Julia sets or the Mandelbrot set. Okay, so let's talk about the Julia sets now. So for the Julia sets, if you fix a complex number c and iterate, so you have zn plus 1 equals zn squared plus c. So the rule is if the sequence remains bounded, then the point is in the Julia set, right? But if it diverges, the point is not in the set. Okay, so that's the thing about Julia sets. So zn squared plus c. Now, example one now, if you let c be equal to minus 1, so it means you have zn squared minus 1, right? So if you start with z naught equals 0, z naught equals 0 simply means that x is 0 and y is 0. So if you start with z naught equals 0, c is already 1, right? It means that z1 is minus 1. And so, uh, if, and z2, So Z2 will be Z1 squared minus 1, which is 0 again. That's just following the what we did the other time. So this is just going to keep repeating. So the sequence is bounded and it belongs to the Julia set. It is bounded in the sense that you have minus 1, you have 0, you have minus. So it is established that you're either going to get 0 or minus 1. So this minimum value you are going to get is 0, and the minimum you're going to get is minus 1 rather, and the maximum is 0. Because of that, because it is that bounded, and it belongs to the Julia set, and then we can visualize that. So imagine that you have this code here for the Julia set. So you have Julia X is you define your X, you define your Y, and then you can have X and Y on a mesh grid. Then you have X to be Z to be X plus IY, and then this is where you define the iterations now. So here you have output is zero Z shape. So this is more like some initialization. So for I in the range for iterations now, you have Z equals Z squared plus C, right? And then you mask it, you output the mask and all that. And then for the complex, you have minus 0.8 to 0.156 for C now. So you are setting C to be from minus 0.8 to 0.156. So the image, you now get the image of the Julia of the complex, right? So if you run that, of course, this C map is the color map, which you can change. So if you run this now, so if you run this, you get the beautiful outputs you can get for that. So this comes out in a jiffy. Yeah, so we have the Julia set right here. So you can see how beautiful. So it's what you see there is just a repetition of uh of the same thing. So if I change this now to say, I think we have cool warm, cool warm. If I change it to cool warm, maybe it will be nicer to the eyes. Okay, it's still looking like red and blue. What if I change it to, I can change it to Viridis. I think there's Viridis. I hope Viridis works here. That Viridis. Okay, yeah, something like this. This is it. You can have Inferno. Inferno is another sim color map. Inferno. You have this. All right. Then you can also have things like blues or greens and things like that. Okay, this is what blues look like. What about if I do greens? So you can keep changing the color map like that. You have greens. Yeah, this is what greens look like. What else do I know? Cool warm, VDs, CVDs. I think there's also CVDs. It's maybe capital C or small. Yeah, this is what CVDs looks like. Yeah, CVDs looks pretty cool. So, I mean, this is Julia set. So this is where complex numbers get artistic. So you can see that you have something, you repeat it, you have a handshake, then it goes big, then you have it duplicated and it keeps going and going on and on like that. So, and the number of you can increase the size, the size there is 400. Well, if you're making 4,000, for instance, I think it's going to take a bit of time, but let's see what happens. That's going to take some time. You have to just continue if it doesn't come out soon. So the size is 400 in this case with 100 iterations. That's going to take a bit of time. But if not, okay, I think we can go on and come back to it later. Yeah. So here now we have for the Mandelbrot set now. So we fix Z naught to be 0 and then we iterate. The other time, right, we fixed Z naught to be we fixed C to be minus 1, right? So here, and then we now let Z naught be 0 to start things out. Okay, I think Julia set is ready now. Okay, it doesn't no too much difference. Okay, I think except that night, like a bit sharper, right? I think it's somewhat sharper than before, like that. In fact, I want to download this so I can use it for my for say maybe screensaver. Yeah. So this is Julia sets. Yes. Then talking about the Mandelbrot set now, we fix Z not to be 0 and we iterate Zn plus 1 equals Zn squared plus C. So the Mandelbrot set consists of all values of C such that the sequence remains bounded. So all values of C so for Julia set you fix the C, but for the Mandelbrot set you let the C keep going. and then you have an escape criterion that the absolute value of Zn is greater than 2, then the sequence diverges in that case. So if we run this now for the Mandelbrot set, we have this. So here I'm using greens. Uh, what did I stop with the other time? CVDs. Okay, let me try CVDs for this and see what it looks like. So this is the Mandelbrot set here. So this is greens. Let's see CVDs. CVDs. So CVDs is a color map. Okay, look at what that looks like. What if we do Viridis? Viridis. Viridis. Yeah, that. Then let me do rainbow. 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 Okay, that's what rainbow gives. Then I let me do um green. Okay, I did greens already. So let me do blues. Blues. Yeah, that's what blues looks like. Then let's do cool warm. Cool warm. I think this is going to throw up an error. I think big C should be small c, I believe. Yeah, this is cool warm. Yeah, so let me go back to okay, what about inferno? Inferno. Okay, this is what Inferno looks like. So here, okay, I stopped with CVDs. Let me come back to CVDs and see what that looks like. So let me stop with CVDs so I can save that. CVDs, CVDs. So there are so many more color maps you can try out for sure. So in this case, now let me also make this one 4,000. And it's going to take a lot of time, but it's okay. 4,000. 4,000, not 40,000 is going to be forever. So this is 4,000 iterations, 100. Okay, so I'll just keep running that and move on with my, oh, it's too much. Something is wrong. Okay, yeah, the comma is gone. The comma was actually gone. So yeah, so I'll come back to that later. Let's move on. So for stability and orbits, so we analyze that Zn plus 1 equals f of Zn. So at fixed points, f of z will be z. So for z squared plus c equals z now. So we can then solve that. So we solve z squared plus c equals z. So that means z squared minus c plus z squared minus z plus c equals 0. So we have different types of behavior. We can have fixed points, we can have periodic orbits, we can have chaotic motion. And the periodic orbit satisfies the fact that f at the kth step, f at the kth step of z is comes back to z. I think that was the kind of thing we saw with when you get -1 0 -1 0. That's some kind of periodic orbit right there. So okay, this is our final result. Let me save this one also. So this is Mandelbrot set. Save images. Mandelbrot set. So we have this. So, yeah, for stability, we've talked about that. And then we can talk about fractal dimension. What's the dimension of fractals? Fractals have non-integer dimension, by the way. So we have the box counting dimension, D equals the log of n all over log 1 over r, where n is the number of boxes and r is the box size. For an example, we have to determine when c is equal to 1 is in the Mandelbrot set. So we want to determine whether c equals 1 is in the Mandelbrot set. So we start with z not equals 0. And if you iterate now, we are talking about z squared, zn squared plus c, right? So in that case now, z1 is 1, z2 is 2, and z3, zn squared plus c. So if c is 1, so we have z1 because z naught is 0, right? So z naught squared is 0 plus 1. We have 1. Then z1 is z2 is 1 squared plus 1. That's 2. Then z3 is 2 squared plus 1. That's 5. So since the absolute value of zn, so as you keep going, it keeps going bigger and bigger. So you can say that the sequence diverges. The conclusion then is that c equals 1 is not in the Mandelbrot set because when you take c to be 1, it keeps diverging. So if c equals 1, it will be in the Mandelbrot set. It means that as you keep iterating, it will be converging towards a given value like that. So c equals 1 is not in the Mandelbrot set. That's exactly what that means. And then we have logistic map, which is one very popular one we talk about a lot. So the logistic map xn plus 1 equals rxn into 1 minus xn. this system exhibits chaos for certain values of R. So this is a well-established one. So, and if we want to visualize that, right, we have R values 2.5 to 4 iterations, 1000, and the last one is 100. We have X, so X, 1 raised by minus 5 multiplied by 1, and we have a bifurcation diagram for that, which is like this. Of course, you can also work with the color plot title, right? Well, I think we can deal with the color here. I think that's where we have no, this is the title. I think it's the plot. Yeah, I think this is what we deal with color. This is black actually. So if I make it B, that changes to blue possibly. So this, yeah, that makes it blue. So we can keep tweaking that. We can make it red if we like. So we can make it red. So this is what happens here. So, and then you can tweak some of these figures to make it uh bigger and bigger, or to make it whatever you want it to be like. So now you see it starts out and it comes to something like 3 point something, and then you have bifurcation means there's a split at some point, and then it gets to a point, it gets to another point again, you have a split, and the splits become so serious that you then begin to have chaos basically. So that's some complex dynamics going on here. In summary, we know that fractals and complex dynamics arise from the fact that Zn plus 1 equals Zn squared plus C. So, and the key ideas we have there is that iteration creates complexity, and Julia set describe initial conditions. Julia sets describe initial conditions, and Mandelbrot set describes parameter space. So chaos emerges from simple rules. Chaos can emerge from order, right? That's one thing that Julia sets and Mandelbrot sets can teach us. So yeah, let's talk about practice problems. As usual, I like to take two. So you have questions 1 to 10 right here, and you have questions 11 to 20, which you can try your hands on. For the Mandelbrot and Julia set, you can actually you can tweak the codes that I used to do your own. So let's go for this now. So here I'm solving problems 4 and 6. Let's see what those look like. Problems 4 and 6. Problem 4 is we want to show that if the absolute value of Zn is greater than 2 for the iteration Zn plus 1 equals Zn squared plus C, then the sequence diverges. And then problem 6, we have that we want to determine whether C equals minus 1 is in the Mandelbrot set by computing several iterations starting from Z naught equals 0. That's the kind of thing we just did, in the notes. So let's go for this now. Um, so we have to determine problem 6 to determine whether C equals minus 1 is in the Mandelbrot set. So we know that if we keep computing with that and we now get divergence, then it is not there. So what we do is we iterate, we iterate, we iterate Zn plus 1 equals Zn squared plus C, starting with Z naught equals 0. So in step 1, right? Step, okay, and then we have we have C already. C has been given to us to be minus 1. So C equals minus 1. So step 1, so step 1 we have Zn plus 1 equals Zn squared plus C. So at step 1 now we have Z1 equals Z naught squared plus C. Okay, we are yeah, plus C, that's fine. Then that means we have Z1 equals Z naught squared. Z naught is 0 and C is minus 1. So C is minus 1. So that means that we have Z1 equals 0 minus 1. So Z1 is equal to minus 1. We keep that. Then we move on to step 2. So for step 2 now, Step 2, we have Z2 to be equal to Z1 squared plus C. C is minus 1, right? So Z2 now, Z1 is already minus 1 squared minus 1, which is C. So that means Z2 minus 1 squared is 1 minus 1. So Z2 is equal to 0. So we have that. So we have 1 minus 1, 0. And then we move on to step 3. So for step 3 now, we have Z3 equals Z2 squared plus C. So that means Z3, Z2 squared is 0 squared. C is minus 1. And then we go back to Z3 equals 0 minus 1. And Z3 is equal to minus 1. So we have that value going up and down like that. Okay, to suit our conscience, we still go for step 4. So in step 4 now, we have Z4 equals Z3 squared. Z3 squared plus C. So that means Z4 is equal to minus 1 squared minus 1. So again, Z4 is equal to minus 1. I mean, that's plus 1 minus 1. Minus 1 squared is minus 1. So we have 1 minus 1. So Z4 again is equal to 0. So we have that oscillation. So it's like we are just trapped between 0 and 1. So that tells us that it's converging. So we see that we observe, we observe a cycle. We observe a cycle 0 to minus 1, minus 1 to 0, 0 to minus 1, and it keeps going like that. So there's no divergence of any sort. So we can then say, thus, absolute value of Zn is actually less than or equal to 1 for all n. So if you keep going, it's always less. So it's bounded by 1. So the conclusion then is that the conclusion then is that this the sequence, right? The sequence is bounded. The sequence is bounded. So C is equal to minus 1 belongs to the Mandelbrot set since it is not divergent. So it's bounded. It belongs to the Mandelbrot set. Okay. So it means if you work with C, you're going to see that pattern that it actually belongs there. That's problem. Oh, okay. I was supposed to do question 4 first, but it's okay. This is question 6, right? Okay, so I'll go back to question 4. So now we see that C equals minus 1 belongs to the Mandelbrot set. So let's do question 4 now. Hmm, problem 4. So for problem 4, so we need to show, we need to show that if the absolute value of Zn is greater than 2 for the iteration, for the iteration, Zn plus 1 equals Zn squared plus C. So you can see this looks very simple, but it leads to chaotic dynamics. Then the sequence diverges. Then the sequence diverges. Okay. So, and the solution to that is this. First, we analyze the magnitude, analyze the magnitude of the next iterate, iterate. So that means if we have we have Zn plus 1 equals Zn squared plus C. So if we using the triangle inequality, we have that the absolute value of Zn squared plus C will be greater, than or equal to the absolute value of Zn all squared, all right, minus the absolute value of C. Okay, so because Zn squared plus C here will have to be greater than when we subtract C from it. So in this case now, if absolute value of Zn is then greater than 2, if greater than 2, then we then have that the absolute value of Zn all squared will be greater than 4. Okay, so that will be greater than 4. So that's if it's more like a square both sides. That'll be greater than 4. And because it is greater than 4, we can then say, so the absolute value of Zn plus 1 is greater than or equal to absolute value of Zn all squared minus absolute value of C. That's established. So for bounded C now, for bounded C. So if C is not exploding, that's what we mean. For bounded C, so once the absolute value of Zn is greater than 2, the quadratic, the quadratic term, the quadratic term will dominate. The quadratic term dominates. So the meaning is that if C is not getting so big that it's going towards infinity, that it's approaching like infinity. So if it's not that big that it's going to infinity, then Zn square will always dominate as the value of Zn is increasing, right? And it's even bounded. I mean, it's even absolute value, right? So it will keep dominating C. So for bounded C now, once Zn is greater than 2, the quadratic term will dominate. And that would mean that the absolute value of Zn plus 1 will be greater than the absolute value of Zn. So thus the magnitude, thus the magnitude keeps increasing. The magnitude keeps increasing such that the absolute value of Zn approaches infinity. So in conclusion, we then have that if the absolute value of Zn is greater than 2, the sequence diverges. It diverges to infinity. And that's what we are told to prove. So with that, we come to the end of this interesting video, and that marks the end of the applications of complex numbers. I think I still have 3 videos to go, maybe some videos about how complex numbers appears in Olympiads and some other areas like that. So watch out for them. So with those 3, I'll probably bring this playlist to a close. So don't forget to try your hands on the 20 questions. Here you have the first 10, of which I've done 4 and 6. Then you have the other 10, which are basically about Julia set, logistic maps, and chaos, like that. Yeah, let me know how helpful this is for you. If there's something else you like in the trial, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, the question is, what exactly are you waiting for? Why not go ahead and subscribe right and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. That gives you some special privileges, like getting to see some videos first or seeing some videos exclusively before other people see such videos, right? You can also request for PDF copies of my notes. You can hang out with me either physically or online. Um, so to discuss whatever maybe interesting you, may interest you on this channel. Ultimately, I mean, you can also ultimately don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.